For lecture number 6, let's talk about the homework problems in assignment number 8. This focuses on steady flow devices. There's your reading assignment. Separate discussions on each of the categories that we've talked about. I've already presented lectures on these topics. You have a collection of problems that I tried to cover without excess problems, so you can work more practice problems if that would make you feel more comfortable. But I wanted you to at least get a little bit of experience of working problems in each of these categories. Okay, so let's take a look at the problems, and I'm just going to set them up. So for example, problem 525 is effectively a hair dryer. Air enters a duct. On the edge of the duct there is an electrical heater. The outside, the exterior, is insulated. They give us information as the air comes in, the temperature and the pressure, and they even give us a volumetric flow rate. And then they don't give us any information at the exit, they just ask us for the exit temperature. We do have the power coming in. The power that's 120 volts times the current is 4 amps. Right, so 120 times 4 watts of power are coming in. So ultimately that energy is coming in, is converted to heat, and we're assuming that all of that heat, now that heat transfer passes through the wall, through the interior surface to the air. The outside is well insulated, and so we'll assume it's adiabatic on the outside. So the heat transfer, this is a heat exchanger example, but the heat transfer is effectively internal. You could do a different type of energy balance where you look at just an energy balance of the air, and then another analysis that includes just an energy balance of the heater, and make a connection between the two, that what leaves the heater is going into the air. But I think it's simpler to just consider the entire unit with one energy analysis. So what I've done for all of these problems is you have the problem statements available to you in the textbook, and I'm only going to spend time setting them up. So you need to make sure that you can, for each of these problems, spend some time, make a drawing, get the information out of the drawing, out of the problem statement onto the drawing, so you can think about an analysis and what's necessary for each of these problems. So that's a critical step that I'm kind of stepping over. I've already completed that process with this little drawing. Okay, so this is an open steady device, air flowing through this, so now we can just start our analysis. We're looking for T2. State 1 is defined, so we could put a star over there. We can even come up with m dot because the flow rate at 1 is given. Let's put a little subscript 1, volumetric flow rate is 1, right? M dot 1 would be equal to the volumetric flow rate at 1 divided by the specific volume. Right, so state 1 is defined, so we can actually come up with V1. So we actually, through a little bit of work, can come up with m dot 1. Let's do conservation of mass. Pretty simple for a single flow device like this. Ultimately, m dot 1 equals m dot 2. Right, that would be no reason to distinguish 1 from 2. We'll just define an m dot. So I'm going to go ahead and write it out. M dot n minus summation of m dot exit is equal to 0 because it's steady. There's only one inlet and one exit. So m dot at the inlet is 1 minus m dot at the exit. Exit location I've identified as 2 above. Has to be equal to 0. So m dot 1 equals m dot 2. We might as well just define that as a single stream, a single m dot. And we can even calculate that, right? That's v dot 1 divided by the specific volume at 1. We would have to be careful with units. This is meters cubed per hour, right? When we're used to an m dot being in kilograms per second. These units for specific volume are going to be meters cubed per kilogram, so this would convert with a direct computation, we would end up with kilograms per hour. So be careful to convert your hours to seconds as needed. So this doesn't actually define state 2. We can do an energy balance to give us another constraint to define state 2. The energy balance is summation of m dot n h plus the kinetic energy plus the potential energy per unit mass. So 1/2 the velocity squared and gz there. All of that's at the inlet minus all of that again at the exit h plus 1/2 velocity squared. I'm running out of room plus gz. I already have that over here. So now I have plus q dot minus w dot equals 0. It's in steady state, so the right hand side is gone. Alright, so if I'm considering an energy balance of this entire unit that would go all the way across, for example, and then so cut across the inlet port, the exit port, and then go across the outside unit of this. The outside of this is insulated, and I have power coming in. So if that's the analysis that we're doing, then that is 0 because it's well insulated. That power, right, is power coming in to the unit, so that's going to be a negative number. So that number is going to be negative EI. Neglecting kinetic and potential energy changes. Neglecting delta kinetic energy plus delta potential energy. So I'm calling those lowercase because this is per unit mass, right? So GZ here and GZ there, I'm assuming that there's no significant difference between those two. Neglecting potential energy, neglecting kinetic energy, I'm assuming there's no significant difference between those two. One inlet, one exit, right? So it's just one m dot that we can factor out. So what I'm left with in this equation is m dot h1 for this term minus m dot h2 for this term minus a minus EI for this term equals 0. So state 1 is defined, so we can get a value for h1. M dot, we've already talked about how to compute M dot. We have a number for that. Those two numbers are given. Right, we have everything except for H2. So solve this equation for H2 gives us another connection at state 2, or actually gives us, for an ideal gas, H is only a function of temperature also. So air as an ideal gas, H is only a function of temperature. Right. Therefore, H2 will give us T2 from the tables. So let's just perform some algebra to solve this for H2. I'm going to divide by m dot takes to H2 to the other side. H2 is equal to H1 plus EI over m dot. Okay, so at this point, you just need to go through and compute, right, and then use the tables directly. So you will need to actually, that one is from T1, but you already know how to deal with properties. Okay, so that's a discussion for setting up problem 425. Let's just continue on and look at other problems. I have every problem set up with the information that's in the problem statement on a drawing. Alright, so problem 429 is simply a horizontal tube with refrigerant 134A passing through it. It's a constant internal diameter of 0.05 meters, so D1 equals D2. It's just literally a long pipe that would allow some heat transfer to occur. At state 1, they give us a quality, it's 0.1. The temperature is 36 degrees, and they actually give us a velocity. It's 10 meters per second. At state 2, it's also defined. The pressure is 9 bar and the quality is 0, so it's coming out as a saturated liquid. It used the wording of saturated liquid in the problem statement, so you have to make the connection that that is a quality of 0. Then it wants us to find m dot, then the velocity at 2, and then the heat transfer. Okay, so the first connection I would make is the kinematic connection, that m dot at 1 is equal to the volumetric flow rate, the velocity, times the area gives you the volumetric flow rate divided by the specific volume. Right, and that area is pi over 4 the diameter squared. So now we just have to figure out what is, for state 1, right, we need V1. Okay, so it's a saturated mixture as a saturated mixture at state 1. Alright, state 1 is defined. So we have a velocity, we have a diameter, and state 1 is defined. So we have a means now to compute the mass flow rate passing through the device. The mass flow rate equals V1 pi over 4 D1 squared over V1. If we did a quick conservation of mass, again, this is a very simple device with a single stream. Right, summation of m dot in minus summation of m dot exit equals 0 for steady flow. Right, one inlet and one exit, so m dot 1 is the inlet equals m dot 2. So we just have the one m dot that we've already figured out a means to calculate. Now how do we get the velocity at 2? The only equation you have where that velocity shows up is this kinematic connection to the mass flow rate, right? So if we can come up with m dot, we can also equate that at state 2. That'll be the velocity at 2 times the area at 2 divided by the specific volume at 2. Alright, so this area is the same area as A1. So let's write it out this way. This guy would be the velocity at 1 times the area at 1 divided by the specific volume at 1. Let those areas cancel, right? A2 and A1 are equal. So now B2 is equal to specific volume of 2 divided by the specific volume at 1 times the volume at 1. And state 2 is defined, right? So we can do some work to come up with that number, and we already have that number. So we have means to compute a velocity at 2. The last question is for Q dot, which is going to show up in an energy balance. So let's write out the energy balance. Summation of m dot h plus 1/2 the velocity squared plus gz minus the summation of m dot h 1/2 the velocity squared plus gz. Right, so this is at the exits. This is over all the inlets, what's coming in, plus q dot minus w dot equals 0. Because it's in steady state. Right? There's no mechanism for power. This is just a pipe. No wires crossing the boundary, no rotating shaft. The boundary is not growing or shrinking, so no boundary work in this problem. We're going to neglect potential energy, change in potential energy. Neglecting delta potential energy. The kinetic energy, we actually have both velocities we have computed. So even though it's likely negligible, I will admit, unless the phase changed, it's likely negligible, we're going to include it because we have that information. And then we have only one inlet and one exit, so we're left with m dot h1 plus 1/2 the velocity at 1 squared, that's the inlet, minus m dot h2 plus 1/2 the velocity squared at 2 plus q dot equals 0. State 1 is defined. We have both of those. Have h1 because the state is defined, v1 is given, h2 is defined so we can get h2, v2 we've calculated that, the m dot, we've calculated that already above. So solve this for q dot is equal to m dot h2 minus h1 plus 1/2 the velocity at 2 minus 1/2 the velocity at 1. Alright, so remember that the units for this are going to be in kilojoules per kilogram. The units for that are going to be in meters squared per second squared. Alright, and 1 meter squared per second squared is 1 over 1,000 kilojoules per kilogram. So you have a units conversion to figure on that. Okay, so that now can be computed. So we've done the analysis work on this to figure out how to solve this problem. Next example is a diffuser. Problem 441. Diffuser with air. It claims to be well insulated. The temperature at the inlet is given. The velocity at the inlet is given. The velocity at the exit is given. It's a diffuser, so the velocity will be lower at the exit than the inlet. And the temperature at the exit is what it's asking for. Okay, so let's go ahead and do an energy balance on this one, and that gives us a connection between state 1 and state 2. Summation of m dot n h plus 1/2 the velocity squared plus gz minus the summation m dot exit h plus 1/2 the velocity squared plus gz q dot minus w dot dE control volume dt, and so it's in steady state, so that's 0. It's a diffuser, there's no mechanism to do any work. Right, it says it's well insulated, so there's no heat transfer. We have no information about potential energy, but we're always neglecting potential energy changes. Neglecting delta potential energy. Be careful, we have kinetic energy, but also the change in kinetic energy is actually the goal of a diffuser, so we can't throw away that term. We've got one inlet and one exit. M dot 1 h1 plus 1/2 the velocity at 1 squared minus m dot 2 h2 plus 1/2 the velocity at 2 squared is equal to 0. Conservation of mass, you can predict that will be that m dot 1 equals m dot 2. So we can just call that a single m dot. So now that equation above, come down here, is m dot 1 h1 minus h2 1/2 the velocity at 1 minus 1/2 the velocity at 2 is equal to 0. So just divide through by that single m dot. This m dot will not be 0. There is a mass flow rate passing through there, so you don't have to worry about the problem of dividing by 0. Divide that through, and we're left with this is equal to 0. For air, right, it's air, air as an ideal gas. H is only a function of temperature. Okay, so we can solve this equation for H2. The temperature at 1 is 270 K, so that gives us H1. We can solve this equation for H2, and then that will give us the temperature at state 2. So H2 is equal to H1 plus 1/2 of the velocity at 2. Is that correct? Minus 1/2 the velocity at 1. 1 there minus 1/2 the velocity at 2 squared. So the temperature goes up in accordance to the change of the kinetic energy. Alright, so remember again that that is a meter squared per second squared is 1 over 1,000 kilojoules per kilogram. Okay, so now we've gone through the analysis part of this problem, and so the actual computations to get to the final answer you can do yourself. Next problem is a steam turbine. I think we worked a steam turbine already in another example, and so I'm not going to spend some time setting up this one. I think it's more important to do a compressor example, so I'll do that next. But in this problem, they do give you an m dot. They give you a pressure coming in at 1 and a velocity at 1. They don't give us another property at 1. In fact, the question is to find T1. At state 2, it's defined, the quality is given and the pressure is given, and a velocity is given there. So we can include the change in kinetic energy in our energy balance. They give us W dot and a mass flow rate. And so with an energy balance, we will be able to solve that for H1, and that'll give us T1. Okay, so I'll let you guys work on that one yourself. Okay, let's set up this problem though in detail as an air compressor, so kind of the opposite of a turbine. Air is the working fluid again, an ideal gas. In this case, the pressure at the intake, so air comes in at 1, at a low pressure, goes out at 2 at a high pressure, so it's 12 times higher, 12 bar at the exit, 1.05 at the inlet. The temperature also goes up a little bit, 300 K at the inlet, 400 K at the exit, and then they also give us a volumetric flow rate at the inlet. So state coming in is defined, also the state going out is defined. We can get any other properties we want. We could get a mass flow rate from this information, right? M dot would be equal to the volumetric flow rate divided by the specific volume at 1. The little subscript 1, that's the volumetric flow rate at the inlet. The volumetric flow rate at the exit will be different because the density is going to be different since it's a compressor. The question is, what is the power required to operate this compressor? And there's also some heat transfer. They give us a heat transfer rate of 2 kilowatts, and they tell us it's from the compressor to the surroundings, so that's energy out. So our Q dot is going to be minus. Okay, so find W dot, neglecting changes in kinetic and potential energy. So let's just do, well, it's a single stream again, so let's do conservation of mass first. Summation of m dot in minus the summation of m dot exit equals 0. Because operating steady state, 1 inlet, 1 exit, m dot 1 minus m dot 2 equals to 0. So there's really a single stream that we could just call m dot. So another simple conservation of mass problem. Let's do an energy balance though, because that's where our power is going to show up that it's asking for. Energy balance would be summation of m dot in h plus 1/2 the velocity squared plus gz minus the summation of m dot exit h plus 1/2 the velocity squared plus gz plus q dot minus w dot is 0. Okay, this is what we're looking for. It takes a power input. That's our unknown. That is given. We cannot throw that away. Right, we have a value for that. Minus 2 kilowatts goes here. We're going to neglect potential energy. It actually says neglect kinetic energy change as well. So we're going to neglecting delta potential energy and delta kinetic energy. Single stream, 1 inlet and 1 exit, so those are the same m dots. So we're left with m dot 1 h1 minus m dot 2 h2. I'm going to go ahead and leave it as q for now, plus q minus W dot equals 0. Right, and these two are the same. That's the same M dot, right? M dot, M dot. So let's solve this for W dot is equal to M dot H1 minus H2 plus the heat transfer. It's kind of logical if you look at this answer. Where does the power go? It goes into increasing H. We're increasing the energy of the working fluid, or also there is some cooling, and so some of the energy that's coming in through the shaft is going out as heat transfer. Okay, remember that this is negative, right? This should be less than 0 because it's a power input. So whatever we get for a final answer, we need it to be a negative number. Okay, so we have a means to compute the mass flow rate, right? So that mass flow rate is the volumetric flow rate entering divided by specific volume coming in, and the state is defined, so we have those two numbers. H1, the state is defined. This is air, right? So those only depend on temperature. Right? That depends on T1. That depends on T2 for air. Right. We're also going to use the ideal gas equation of state to come up with that V1. Specific volume, sorry, the M dot is the volumetric flow rate over specific volume. To get the specific volume, use the ideal gas equation of state. Go to the tables for air to get those two H values, and then that number is minus 2 kilowatts. Okay, so it takes time, notice, on each of these problems just to go through this analysis part to figure out what to do. It also, what you're not seeing is it takes time for me to create that while reading the problem statement. And then again, it's now going to take you more time to actually compute to final numbers. I'm going to save I think I'm going to save this one for last. It deals with the incompressible flow. I'm going to talk about this heat exchanger. So here's a heat exchanger, problem 475. Refrigerant 134A is passing through one pipe network. Air is passing through another pipe network. The drawing looks a little bit different. It looks like it's more of a heat exchanger. A radiator design where you have refrigerant passing internally through pipe flow and air with a fan over the outside of it, but it's effectively the same conceptually. To say I have some air passing, isolated passage of air, very, very close to an isolated passage of refrigerant, so there will be heat transfer between these two. In fact, in this case, we can look and see that the air comes in at 305 K, it goes out at 295 K, so the temperature of the air is dropping. So there must be heat transfer out of the air into the refrigerant. But that heat transfer that's occurring is internal to this entire unit. So it's easiest to do an analysis, a energy balance of this entire unit. The outside exterior of this is insulated. Insulated exterior on the outside. The refrigerant, the state is given at the inlet, the state is given at the exit. The air, the state is given at the inlet and at the exit, and for the air, the mass flow rate, the volumetric flow rate is given. But it's easy to convert that since state 1 is defined to the mass flow rate of the air coming in. Okay, so conservation of mass would say that there's an m dot over here, right, and then an m dot over on this side. Conservation of mass, let's say single stream m dot 3 equals m dot 4 equals m dot, let's call that m dot 134a. Alright, single stream. That's my way of communicating the reduction of conservation of mass. And you're okay to do this as long as you communicate something. Single stream, steady. Let's put the word steady in front too. Steady single stream for the air. So m dot 1 and m dot 2 are the same. So that's just m dot of the air. And that m dot of the air, we've already said we can compute with the volumetric flow rate divided by the specific volume for state 1. This is for air, right? For air. Alright, so as an ideal gas, PV equals RT. P1V1. So use that. Pressure and temperature are given to solve for the specific volume. So we can compute m dot for air. Now let's look at the energy balance for this. Summation of m dot n. H plus 1/2 the velocity squared plus gz minus the summation of m dot exit. H plus 1/2 the velocity squared plus gz plus q dot minus w dot equals 0. Steady, so the right hand side is gone. There is no mechanism for any work, and we're considering an energy balance of the entire unit, right? So it is the exterior is insulated. Let's put well insulated. Alright, so that's gone. All the heat transfer is internal in this problem. Let's neglect kinetic and potential energy for this heat exchanger. Neglecting delta kinetic energy and delta potential energy. That was supposed to be a K. Kinetic energy and potential energy. And so I have m dot air at 1 is what's coming in. So we got to keep our numbers consistent. Air is coming in at state 1. Air goes out at state 1. So I'm going to do m dot air H1 is coming in. Also coming in is m dot refrigerant 134A times H. The refrigerant comes in at state 3. H3. Minus going out for the air is at state 2, and going out for the air, for the refrigerant, is state 3, and that's the only thing left in our equation, so that equals 0. M dot air times H of the air coming in. Probably could put a little subscript air there, right? That's refrigerant there. That's air. And that's refrigerant there. Okay, the states are defined for all of these, right? So we can get an H value. All states are defined. So we can do the work to come up with those H values. We've computed W dot for the air. We simply need to solve this for M dot of the refrigerant. M dot refrigerant 134A is going to be equal to, let's take these two to the other side. It's going to be equal to M dot air times H1. Actually, let's do H2 minus H1 since it's going to the other side of the equation. So that's for the air divided by H3 minus, that should be an H4, right there should be a 4. That was the other exit. Minus H4, and this is for the refrigerant 134A. Okay, so we have enough information to do the work to compute number of values and then substitute for each of those. Lastly, let's set up problem 70 is a water pump. They give us the state coming in, the pressure and the temperature is given. So 1 atmosphere pressure, 14.7 psi, comes in 180 degrees Fahrenheit, so it's hot water. It goes out, the pump increases the pressure from atmospheric pressure to 120 psi. And the question is, what's the temperature at the exit? They give us that the pump is well insulated, and they give us the power input to the pump is 1 over 35 horsepower. So it's a fraction of a horsepower. And since it's an input pump, the power is going to be an input. That would be a negative number. They tell us to assume it's incompressible with a constant density specified. Remember that this density is 1 over the specific volume, so we can calculate the specific volume from that given information. And we can also assume a constant specific heat. The specific heat is 1 BTU per pound mass. And so the question is to find delta T when we're neglecting kinetic and potential energy in this. Conservation of mass is going to be a single stream, m dot in equals m dot out. The temperature variation is going to show up in the energy balance. Let's write the energy balance equation. Summation of m dot n, h plus 1/2 the velocity squared plus gz. Summation m dot exit, h 1/2 the velocity squared plus gz. Q dot minus w dot is equal to 0 because it's in steady state. That 0 is the dE control volume, dt term. Equal to 0 over here because it's in steady state. That number is given to us, so we know what that is. It says it's well insulated, so that's equal to 0. Neglect kinetic and potential energy changes. 1 inlet and 1 exit. M dot 1 H1 minus M dot 2 H2 minus W dot is equal to 0. Single stream M dot 1 is going to equal M dot 2 is equal to M dot. Conservation of mass. M dot 1 minus M dot 2 equals 0. M dot 1 equals M dot 2 then equals, let's just define that as an M dot. There's a single M dot passing through the device. They give us the volumetric flow rate at the inlet, and state 1 is defined so we can get the specific volume. Alright, so this is equal to volumetric flow rate at 1 divided by the specific volume at 1. Right, this is for the inlet water. So that state is defined. We have the temperature and the pressure there. So we can come up with an M dot. Now let's take this and adjust this equation a little bit. M dot H1 minus H2 is equal to the W dot. State 1 is defined, the mass flow rate we have, and that one we have. Right, we can solve for H2 to try to give us the temperature at 2. Gives us a second property. This is a second property at state 2. Alright, so H2 is equal to W dot. Let's see how this is going to work. H2 is going to be equal to H1. Then I have minus W dot over M dot. Did I do the algebra right for that? I think so. And remember that power is a negative number, so this will ultimately increase the value of this. Okay, so now we need to come up with H values. So this is an incompressible substance since it's water and both of those states are defined. So they've asked us to evaluate, assuming incompressible, constant density and the specific heat given, assuming a constant specific heat. So instead of working it this way, we can go back and make an evaluation, express delta H in terms of temperature, and then solve this directly from temperature. Okay, so if H is a compressed liquid, then remember that H is equal to U plus PB by definition. That's what H is. If it's incompressible or a compressed liquid, this is only going to depend on temperature. So that's U as a function of temperature plus P times B as a function of temperature. Actually, that's going to be UF at the temperature, and that's going to be VF at the temperature, and that gives us an evaluation for H. So what we can do is say H1 is equal to UF at T1 plus P1 times VF at T1. Alright, so P1 is known, temperature at 1 is known. We can come up with a value for H1, and then for H2, that's UF at T2 plus P2 times VF at T2. Right, that T2 is unknown. And so there's really two properties that T2 affects. So what you have to do in this case, you can solve this, use this expression for H2 with this up above. This is also equal to H1 minus V dot over M dot, right? That W dot, excuse me, is minus 1 over 35 horsepower. And we have a means to compute, I don't have a number for it, but you have a means to compute that M dot. So now what you could do is you could go to the tables, make a guess for what T2 is, right? With that T2, compute a U, or determine a UF and a VF, put it into this equation to see if it satisfies this. Eventually you'll be able to find a T2 through iteration. So we could find T2 via iteration with tables. For water. Or we're going to assume constant specific heats. Or assume constant specific heats. In which case we'll go back to H, what was the equation? H1 minus H2 times M dot is equal to W dot from our energy balance. And we can just evaluate that change with constant specific heats. So this would be equal to, it's going to actually be U1 minus U2, sorry I got that backwards, U1 minus U2 plus P1 B1 minus P2 B2. Let's just do it as a direct substitution so it's easier for you to see. We'll do U1 plus P1 B1 for state 1 minus U2 plus P2 V2 for state 2. So that goes in place there. And so this is U1 minus U2 plus P1 B1 minus P2 V2. It's incompressible. V1 is approximately V2. We'll factor that out. This is approximately C times delta T if we assume constant specific heats. Constant specific heat there, so we end up with m dot times C. It looks like T1 minus T2 plus V1, or the V, P1 minus P2 is equal to W dot. I think we had a discussion before during Zoom at which I suggested C times delta T was H, but actually you have to include the pressure part, right? The V times the pressure part of this. And so that is 1 over the rho given. Okay, so we could solve for T2. Can now solve for T2. There's another problem that involves, I think, a passive water heater that has liquid water coming in and liquid water going out. So ultimately, you're going to have an H1 minus H2 evaluation in that as well. So it'll be similar that you'll need to include the internal energy plus the PV term as well. I have another discussion that I was going to include in this where I'm going to talk about incompressible substances, but I'm already at 47 minutes for this video, so what I'm going to do is actually create another video that just focuses on incompressible substances. And for those who don't need that, you don't need to look at that video. You just need to make sure that you can evaluate properties, whether they be ideal gas, incompressible substance, or our pure substance, superheated vapor, or saturated mixtures.